acids as fuel. To do this, you have to take the amino group off, and then the carbon backbone has to be converted to the I hate this one, TCA. It's like tricarboxylic acid cycle. I just usually call it the Krebs cycle. Intermediate. So, this use is dependent on conditions. So, I'm not making you memorize which ones go where. That's not happening. Quiz 6 relies on a couple of figures to help you walk you through where things go in and where they can and cannot be converted. But before we do this, let's pause for 1 second because I'm switching themes. So one more time. Nitrogen amino acid metabolism has to do with moving stuff around so you can get different amino acids, right? So you have amino acids for protein synthesis. You're moving stuff around, you can get different amino acids. Now you can be wanting different amino acids because only certain amino acids can enter the Krebs cycle, but this is about moving amino acids around so you make different amino acids.
Right?
Yes, you can deaminate, yes, so you can get, and that's, yes, but so yes, making, losing in relative proportions. That's the nitrogen theme. The carbon theme is when you get rid of the nitrogens, then you have to convert it to another step, which is a tricarboxylic acid cycle intermediate. What that means is, let's just look at the figure before it'll be easier to see. Okay, so this is figure 1410. Okay, so there on the quiz, I talked a little bit about there's this word called anaplerosis, and that anaplerosis word is right down here. And I walked you through what it is in the quiz a little bit. So this is making, from amino acids, new Krebs cycle intermediates, right? Okay, so this, I know this is familiar. I know everybody looked at this. When you learned it, you learned that you go from acetyl-CoA to citrate, right? And then you go through all the different intermediates, and when you go through, you produce certain certain ATP at certain steps, right? Mm-hmm. And then you get all the way to oxaloacetate, and then you can go run through the mitochondria for complete oxidative phosphorylation, right? Somewhere in the back
If
of
we
our
don't
heads.
have this memorized, that's okay.
No, you don't need this memorized. I don't want this memorized.
Or
You
the
already did
steps
that.
at all.
Yeah, you already did that.
Okay.
I just assume that you know it somewhere or can find a picture of it so you can follow along. Okay, so you have two options, right? So you can enter this at the beginning. These amino acids make acetyl-CoA. Acetyl-CoA enters at citrate. This is what's considered the beginning of the amino acid cycle. This is the first step, and when you run through, you get maximum ATP, right? This is how to get maximum. So for carbohydrates, you want to start here because you'll be able to get ATP at all of the right steps and make as much as you possibly can, right? This, for amino acids, only some of them can get broken down into acetyl-CoA. And ironically, the ones that get broken down into acetyl-CoA do not produce energy, okay? The reason is because if you go here and you have to go all the way around the cycle, you're using something up. All right, I know that sounds a little weird. Let me read it from the book and then it'll make a little more sense, okay? Okay, so gluconeogenesis, the production of new glucose, right, from non-hexose precursors, may occur only from those amino acids that in their metabolism produce intermediates of the cycle that may be converted to oxaloacetate, thus providing an additional cycle intermediate and permitting the withdrawal of the molecule for gluconeogenesis. The provision of new cycle intermediates is referred to as anaplerosis. The metabolism of leucine or lysine, up here, does not have an anaplerotic effect. Although carbon from these amino acids enters the citric acid cycle as acetyl-CoA, right, which reacts with oxaloacetate to produce citrate, this reaction does not expand the pool of cycle intermediates. So, in English, what does that mean? Here's acetyl-CoA. For acetyl-CoA to make citrate, oxaloacetate is hanging out here, right? So oxaloacetate reacts with acetyl-CoA to make citrate. So you just used up your oxaloacetate. You used it up to run the cycle. You're not going to be able to send it out to make new glucose, okay? Because you just took it. It was sitting here, and instead of sending it that way, you took it over here to make this. Does that make sense? It's sitting here. It can't, you only got one, what else are you going to do? If, on the other hand, you are isoleucine, you enter at succinyl-CoA. So you're already halfway through. You go do. You get to oxaloacetate, right? So you didn't have to use up your oxaloacetate to get here, right? There was already one sitting here. But because you didn't enter up here, you entered down here, there's still one sitting there to react with new acetyl-CoA, so you can just go here, and then you can become glucose. So to say that one more time in a slightly different way, because this is important. Oxaloacetate has a lot of options, right? It can become glucose, or it can join with acetyl-CoA to run the Krebs cycle over and over again. If you are running the Krebs cycle, you are generating energy in the form of ATP for storage, right? When we are in a high energy condition, we're making ATP for storage. When we're talking about gluconeogenesis, we are not storing ATP. We want to make new glucose. The only way we can make new glucose is to take, from the Krebs cycle, is to take the oxaloacetate and send it out. If you have acetyl-CoA over here, it has to join with oxaloacetate to form citrate. So these don't make any new, they just used up the oxaloacetate that was already here, right? It used up this oxaloacetate, so you have to run all the way through to get some more. If you join in down here, this oxaloacetate is still sitting here, so you're going in this direction. Does that make sense?
And glutamate, the same thing. Like
exactly, anything that's not
below
here.
Citrate.
Right. Now if you join in all the way up here, you're going directly to oxaloacetate, and then you can go directly back out.
And I'm sorry, how do the, like I'm seeing all of those amino acids, they're just being turned into acetyl-CoA by
So yeah, there's a
process.
multiple step process. This is a summary of multiple step processes. What this is showing you is where each amino acid that we talk about enters the citric acid cycle. Question?
Was it